Excellent. So this is not going to be a presentation filled with slides, but I needed to have some little slides because I wanted to start off with some introductory topics, just to make sure that we're all on the same page. Some people may be very familiar with TLS, other people may not be. So I didn't want to assume a specific level of experience. So to start off with, hi, I'm Tom. I work as an engineer at DigitalOcean. I work in the security org with Ross and occasionally make his life hell. The rest of the time, I make everybody else's life hell. One of my many day jobs is managing DigitalOcean's PKI infrastructure. And a lot of that management and a lot of the integrations with our PKI infrastructure are written in Go. So it's timely, and I think I know enough to be able to talk about it sensibly. So let's get rolling. Ssl Tls Https. We've all used it. You see the little padlock on your web browser. That's what's happening. What this actually provides is a secure, confidential communications channel between you and the server that you're talking to. Intermediate systems may be able to know which server you're talking to in terms of IP addresses, but they won't know exactly in terms of host names, or, I mean, they may still in terms of DNS lookups, but in terms of the actual things that you and that server talk about, that's all encrypted. And that is done using a protocol called TLS. That protocol, by default, only provides the identity of the server to the client. In other words, me as a client, me as a browser, when I connect to a server, the server, as part of this thing called the TLS handshake, gives me its certificate. Its certificate is in a format called X509. I'll show you that in a second. The important thing is that I get, as a client, I get to verify that I trust the server. So that server certificate is considered valid if I trust the issuer of that certificate. In other words, I trust the company that actually provided that certificate to the server so it could give it to me. If the certificate has not expired, and if the certificate matches the server's hostname and domain. So, if I'm doing www.google.com, then the name in the certificate somewhere has to be www.google.com. If it's not, then it's the wrong site. Somebody's impersonating Google. I should not trust that certificate. Sometimes when you're doing HTTPS internally inside an organization, your browser will pop up, the server is not trusted. Would you, do you want to bail out, or do you want to add an exception? And it's usually because it's a test server and it's giving you a certificate that is like localhost or something else, or it's for the wrong server. Within companies, you see that a lot. But if you see that on the internet, there's definitely something wrong there. You probably shouldn't talk to that server. There's this thing called mutual TLS. So the standard protocol that your browser uses to a server is just, it verifies the server. The server still does not have a clue who's talking to it. It may know the IP address if the universe cooperates and it gets the right IP address, but that's pretty much it. It's really good for the internet. It's not necessarily as good inside environments that require a high level of trust, company intranets, that kind of thing. Production systems. The TLS protocol provides client-to-server authentication using certificates that a client provides to a server. So the client verifies the server's identity, and the server gets to verify the client's identity using the same rules as I mentioned previously. The server can also add additional rules, like only certificates issued, only clients with this particular pattern inside that their certificate are allowed to talk to. It's really difficult on the internet because it requires every client to have its own certificate. There's been a number of places that have tried to distribute it. A number of people have tried to foist that kind of thing on everybody else. It breaks down because PKI, or public key infrastructure, is actually a really hard problem. And it's a very hard problem to solve for everybody on the internet. If you're within a company and you have a much more constrained audience, that problem becomes a little bit easier. So X509 certificates. Most of the time, for most systems, except for Java, certificates are encoded in this format called PIM. As you can see, there's a little header, begin certificate and end certificate, and then a whole bunch of base 64 encoded stuff. Certificates themselves are actually a very specific binary data structure, and PEM files just make it really easy to encode certificates as text. And PEM actually stands for Privacy Enhanced Mail. It was originally built to transfer big files over email. When you decode a certificate, and you can decode a certificate using tools like OpenSSL, you get something that looks like this. This is, the structured data that you get in there. You get a certificate, it's got serial numbers and versions, you know who issued it, you know the canonical name of the server that actually is supposed to have that certificate. It'll tell you a lot about its key. It will also tell you that this server the certificate is also valid for other things, not just, this server.example.com, but it could also be valid for example.com, for server.example.com, and for localhost, for testing, sure. In production, you probably never want to have localhost or the IP 127.0.0.1 in a production certificate. That's really bad. Okay, so that's a decoded certificate. Servers fling them at clients, clients parse them, decide that they trust the server or not. So first steps at a public key infrastructure. There's this thing on the internet called root certifying authorities, or root CAs. And there are places like Let's Encrypt and DigiCert and Komodo and everybody else who can issue a certificate. These are very large companies, very large public organizations. They're trusted by browsers and makers of operating systems, to the point where their actual certificate, their public certificate, is actually included in browsers inside Mozilla or inside operating systems. Which means that when something that's using that operating system sees a certificate that has been signed or has been created by one of these trusted entities, it goes, yep, I'm going to trust that certificate. There's also this thing called intermediate certifying authorities. Some of these big players, having full control over a root certificate is actually a really big problem. So what usually happens is that root certificates are created, and then the private key is like locked inside vaults behind walls and fences and folks with guns and dogs and all sorts of other things. Because this is the ultimate prize in terms of, breaking through and impersonating another system. Equally trusted are these things called intermediate CAs that root certifying authorities will often delegate capabilities to intermediate certifying authorities. Some intermediate authorities are only allowed to create certificates for web servers. Others are only allowed to create certificates for clients. Others are only allowed to create very short-lived or very long-lived certificates. All sorts of rules can be around intermediate certifying authorities. And most of the big players, like for example, DigiCert, if you ever see a DigiCert certificate, it'll actually be a certificate chain. So it will be the certificate that you wanted that was generated, plus DigiCert's internal intermediate certifying authority, because DigiCert's root certifying authority is on every machine on the internet. So when a server receives that kind of a certificate, it can do what is called certificate chain validation. In other words, it looks for the certificate that it received and ensures that it's valid in terms of it hasn't expired and it matches the server that it's supposed to be that you're supposed to be talking to, but it's not yet valid because it can't figure out who actually signed it. So one of the things that comes with that certificate is the certificate of the intermediate signing authority. And then you follow the chain of certificates down to something that you really do trust, which is the root certifying authority. If you can't find the trusted root certifying authority, then you just go, this is not a valid certificate, bounce them out, show a warning to the user, or if you're an API program, actually refuse to work. So yeah, if we're looking at PEM format certificate chains, it really is just, first certificate in the chain is the certificate of the server that you're supposed to be talking to. Second certificate, and any subsequent ones are the intermediates down the chain. There's not, some places can have multiple intermediates. I think the biggest I've seen is 6. That was a weird setup. So running your own public key infrastructure, it works fine on your machine. Running it in production gets a little bit more exciting and painful. If you're an organization, DigitalOcean or bigger, or even smaller, if you really want to go through the trouble, then running your own public key infrastructure makes it really easy to distribute internal certificates for both clients and servers. And that means that you can begin to ensure trust that, this system is actually owned by DigitalOcean because it's the only thing that could have this particular certificate and key, and it talks to this system, and it's the only thing that could have that. And they can trust and they can verify each other. And then you can do all sorts of audit logging to kind of say, or record that this thing talked to me, presented this certificate, it came from this IP address, and if there are any issues, you can start sending alerts. Your security organization's monitoring systems can kind of say, hey, things are presenting the wrong certificates. All sorts of other things can happen. What we're going to be talking about during this presentation is something called HashiCorp Vault. Vault is, it's a single binary you download from the HashiCorp website. I like to think of it as a sort of a security and cryptography kitchen. It provides you all the tools and all the ingredients. You still need to figure out how to make a meal. For us, or at least for the purpose of this talk, what's actually interesting is they have this thing called a Pki Engine. And that's what we're going to be looking at to run a local certifying authority. Vault itself is ridiculously easy to run in dev mode, totally isolated, standalone, not talking to anything. It's really easy to get started, get familiar with Vault's API and the capabilities of Vault itself. When you want to use Vault in production, it gets a little bit more interesting because, when it's running in standalone mode, it remembers everything, but when it shuts down, it forgets everything. If you want things to remain in memory, then it needs to have a backing store, which could either be a relational database, or HashiCorp recommends console. And if you want to run things in high availability, then you will run multiple Vault nodes and multiple console nodes inside a Raft cluster and all sorts of other things. So just getting it up and running is not a trivial task. If you script it, if you automate it, it does not need to become a full-time job. At least that's what I tell myself. So it's time to see some code. So what we're going to be doing is we are going to be going through the code in a project that I created for the purpose of this presentation, for the purpose of talking to where are you? For the purpose of talking to engineers about mTLS and how to set that up. So that code is available on GitHub under the DigitalOcean banner, and it's an entire thing called an mTLS Tech Talk. It contains both the actual presentation, the meat of the presentation that I'm going to be talking about, and all the code necessary to make everything run. While this code shows all sorts of command line commands, I don't really want to type that much, so there is actually a make file inside this project that encodes all the common commands, so that I don't have to remember. And if I'm doing a live coding thing like I'm about to do, I don't actually have to fat finger too many things. So saying that, the first thing that I want to cover is how to do TLS in Go, because this is a Go meetup and we're going to be talking about Go things. So creating a HTTPS service in Go is not actually a particularly difficult thing. Go is one of the nicest languages I've actually come across to create servers and clients that can not only do TLS but also mTLS. We are actually just going to be using straight libraries from the Go standard library. The Go mod file for this is actually empty. We're not using any third-party stuff. All of this code is something you get with Go when you actually install it. So first things first, we want a HTTPS server in Go. Well, a HTTPS server in Go requires a couple of things. It needs to know that it has a certificate file, and it needs to know its private key, so that when a client talks to it, it can begin to create a secure communications channel with that client. If you want to validate incoming certificates from clients, you also need to have the certificate of the root certifying authority that is the ultimate originator of the certificates that are going to be provided to you by clients when they connect. Because for mTLS, client verifies the server, but the server also verifies the client. Kicking all of that off is actually not particularly difficult in Go. To get the certificate for the client, to get the root certificate, requires a few relatively innocuous Go commands. What you really want is a populated certificate pool. Usually that is populated from your operating system's certificate libraries that Go will actually go and look for. But you can override that if you're doing a custom certifying authority, and that's exactly what we're going to be doing here. So we create a certificate pool, we read the file as an encoded PEM file. We then go and we say, okay, well, we're going to grab all of the certificates inside that PEM file and we're going to stick them into the certificate pool. That's cool. That's it. Done. We now have a store of certificates that this particular instance will actually trust. Once that is done, you can go ahead and just load up the key pair. Again, Go makes it really easy. Load the certificate and key file in using a standard library function call. It returns you this big data structure called the server certificate. It's great because everything else then uses it. You configure the Go HTTP server to say, these are the certificates that you're allowed to present to clients when they talk. If you this setting basically says, if you get a client that does not present a server certificate, that does not present its own certificate, or presents an invalid one or anything else, just reject connections from that client. And use this root client pool to verify the client certificates. Once that's done, you just simply create a standard HTTP server like you would normally. You give it a handler function, you give it the TLS configuration, and then you start it, and off you go. The handler is actually probably the least interesting part of this code. All it really listens to is a GET request with an optional parameter called name. If you get it, then you'll get to see hello world, hello whoever, and it gets plain text output. The client certificate itself is almost an exact mirror of the server code. The client, because it's going to be verifying the server, needs to know what certificate to use to verify the server certificate. Because it's also going to be providing its own certificate and key, it needs to know those. And then there's an optional little command line flag, so you can say hello, whatever. So again, parse the flags, create a certificate pool, read the root file in, stick them into the pool, everything's cool, generate a key pair, generate this big client cert data structure. The client code gets a little bit more nested as you try to configure it for TLS, but it's not that different to the server. You create a client, you give it a HTTP transport with a TLS config that says, use this certificate pool to actually verify client, to verify the server. And when the server asks, here is your certificate that you need to send to the server. After that, it's just a standard HTTP call, make a GET request to a server. If we gave it a command line flag of a name, then send that name as the command line flag as a query parameter. Read the response, print it to standard out. That's it. So HTTPS in Go, even mTLS in Go, is really, really ridiculously easy. Comparing this to, say, code that you'd have to do in Java, this is nothing. This is lovely. This is really quite nice. Oh, it gets a little bit more verbose because, again, Go requires that you check errors, which is a really good idea from somebody, old grumpy person like me, who comes from the operations side of things, because everything can fail. And then it's up to for you to decide whether or not you accept that failure, do you bubble up, or you die yourself. So Go makes it really explicit, and it's probably a whole lot more explicit than old Java's way of throwing checked exceptions everywhere. Because you pretty much ignore them and wrap them in a runtime exception anyway. So what we want to do is we want to spin up Vault, because we're going to be using, there's lots of tools that you could use to create certifying authorities. You could use OpenSSL itself. You could use CFSSL from Cloudflare. There's a bunch of other command line tools that you can use for local development. But because we're talking about Vault, we're actually going to use it. We're going to use it locally in dev mode. So again, make file target. Basically, just fetch Vault, start it up. We absolutely want to use this dev flag because it shortcuts a lot of the authentication requirements and a lot of the validation requirements. If we wanted to talk about Vault policies, access controls, app roles, and everything else, we could probably do this in another presentation, because it's not only a presentation's worth of stuff, it's probably an entire workshop worth of stuff. So we're going to shortcut all of that and just use the dev mode. Important thing, we are using dev mode. We are using root tokens for authenticating with Vault. This is a really good idea locally. This is a terrible idea for production use. Even as a Vault administrator, I very rarely use, maybe once a year I need to use a root token to do something. For the rest of the time, I don't even have access to root tokens. In fact, we don't keep root tokens. We delete them and force them to be recreated when we need them. And that requires a couple of people to actually approve. So there's some really good security around it, but for the purpose of this presentation, we're just going to use root tokens. Okay, so let's make this happen. So we are going to go and run Vault. That sounds like a good idea. Waiting for curl. Starting Vault. There we go. That's it. Vault's running. No big deal. So what we probably want to do, though, is we want to be able to create a root certifying authority. This is a presentation about TLS, so we need a root certifying authority. The way to do that is to actually issue a Vault API command. In this particular case, a number of Vault API commands. What we really want to do is we want to enable the PKI secrets engine at a specific path and give it a relatively long lease period for timeout period for certificates. We then want to actually go and do some nice configuration of that Pki engine so that the appropriate URLs that are required for TLS validation and what they call certificate revocation list validation are actually added into its configuration. Certificate revocation is actually an interesting topic all on its own. You know, sometimes within internal systems, you absolutely want it because, say, for example, you issue a relatively long-lived certificate for a system or for a team or for a user, and that user leaves the company or is fired, or that service is compromised, you may wish to be able to cut off its access a lot sooner than the certificate would normally expire. Using certificate revocation, you can actually do that. There's a Vault API command where you can actually say, I want you to revoke this certificate, and it goes ahead and does it. And then if anything then tries to connect and using that certificate, you can actually specify to certain clients, go and check the revocation list in the certifying authority, and it will go to the certifying authority. It will go to Vault and will say, is this certificate revoked? And Vault will say, yes, it is. Can't talk to it anymore. It's really good. However, in Go, certificate revocation lists are not checked automatically. Go has all of the machinery to do that. It's just not wired in. So there's a little bit of stuff you have to do. We're not going to do this in this presentation, but if anybody's interested, I could probably show you how to do it. Okay. What we then want to do is we really want to write out the root certificate so that we can actually give it to the client and server. The certificate doesn't actually do anything until something can use it. The next thing that we want to do is we want to create, Vault has this concept of roles. Everything in Vault is either a role or a token or a combination thereof. What we want to do is we want to create this thing called the Pki Role, which is the thing that has all of the policies on how to generate certificates. In this particular case, we want to allow it to create bare domains. We want to limit it to creating certificates that are for example.com. It's okay if you want to generate a certificate directly for example.com. It is also okay if you want to generate a certificate for a subdomain, tom.example.com, no problem. Because it's local and it's testing, we're going to say, sure, if you want to allow the creation for localhost, go nuts. Because it's again for local, or sometimes it's useful for other reasons, you want to say, hey, my certificates, my servers don't actually have host names. I don't have an internal DNS, all I have are IP addresses. That's okay. We can use this Pki role to actually allow Vault to generate certificates just for an IP address. Enforce host names is usually a good setting. You can provide all sorts of horrible and funky characters into host names, otherwise that will break clients and browsers and all sorts of other things. So there's a limited character set. You probably want to just say yes most of the time for this. Certificates should only live for 720 hours, 30 days. Use RSA keys. There are many key types. We'll just stick with the default. 2048 sounds good enough. You can go higher. Whether or not you really need to is a conversation for people with lots of crypto experience. All right, so that will actually spit out a so the previous command spat out a little JSON file called root.json. What we want is we actually just want the certificate out of that piece of JSON, and we want to write it out into a little file. And then we get to see that it actually has worked. So let's run that. So this is setup root CA. So we're going to run that. We're going to go make setup root CA. There we go. We have a certificate. It's been created. It was created. The issuer is a local root certifying authority. It's created for itself. If you have a look at the root JSON file, the Vault spits out an awful lot of things that you can actually then do, including the serial number for the certificate. It's really useful to remember those serial numbers or store them somewhere so you can go and look up certificates by serial numbers or just revoke them if you need to. The root CRT is exactly what I showed you in the slides. It's just a PIM encoded piece of base64 binary stuff. All right, so we have the certificate. Okay, well, if we've got a certificate, so what we now want to do is we want to issue a certificate for the client itself. And the way that we go about doing that is, again, a bunch of little API commands. So we can issue the server certificate. We just basically say, hey, I want to write to a specific endpoint. In this case, the issue for the service. The common name that we want is for www.example.com. Because I'm going to be running this locally, localhost and 127.0.0.1 are actually reasonable to have in the certificate. Otherwise, I'd have to be doing a little bit more configuration. I don't want to do that. Spit out the output into a JSON file, and then process that JSON file to grab the certificate and the private key. So let's do that. Make issue server certificate. Again, we have a server certificate. It is for, where are we? Subject canonical name is for www.example.com, but it does allow localhost www.example.com, and it also allows 127.0.0.1 as an IP address. Cool, it's exactly what we wanted. Because we're doing mTLS, we probably want one for our client. So hello, Alice and Bob. Every piece of every cryptography white paper and thing talks about Alice and Bob. So we're going to talk about Alice and Bob too. So we're going to issue a certificate for Alice. And again, it's just another Vault API command. Basically say to Vault, I want you to issue a certificate for Alice. I'm not giving it any alt names or IP sans because I'm not trying to make Alice into a server. I just want Alice to have a certificate that says, hi, I'm alice.example.com. So we're going to write that out. So make issue Alice. Cool. The certificate has been generated, and it was generated for alice.example.com. All right. So at this point, we can actually go ahead and start up the client and the server. So what we're going to do is we're going to start up the server. Go make run which run mTLS service. That's the one. So we basically run that main.go file, and we give it the cert and the key. The root certificate is the default that we already had in our code, and it says, yep, I'm started. And then we can go ahead and actually see if we can connect to it. So we can go make run ls client. Again, it's exactly the same thing. We just basically run the client code and the server said, hello, Alice. Done. That's it. I should go away now. We have mTLS and Go. Client trust server, server trust client. They get the right response. Well, what about Bob? Well, if we want Bob, we can also generate a certificate for Bob. So that's cool. Make issue Bob certificate. Yay! We have a certificate issued for bob.example.com. And we can go and we can do make because the server trusts the root certifying authority, it will trust both Alice and Bob, and it will respond to them appropriately. Now the question becomes, what if we don't want to allow Bob to access a service for Alice? This is an Alice only service. If you are not an Alice, you should not be here. The standard answer in a lot of places is to run multiple certificate authorities, right? You will have a certificate authority that will only generate certificates for Alice's, and another certificate authority that will only generate certificates for Bob. They will only, the servers will only trust Bob certificates. The clients will only trust Alice certificate. You know, you get to decide how you want to do that trust. So that way, a server that only trusts an Alice will never trust a Bob, because it will get a Bob certificate. It will say, I don't trust your root certifying authority, and it will tell it to go away. That's good enough for lots of things, and it's sometimes the only thing you can do with a lot of third-party software. So you have some code that will do mTLS. You have some service that will do mTLS, but it can only do it based on certifying authorities. Fine, create very specific certifying authorities for it. Provide clients with the appropriate certificates so they can trust each other. Nothing else that hasn't been able to get access to those certificates will never be able to talk to it correctly. It works. What if we want to keep our root certifying authority? Well, this is where we can actually now get down into the interesting path where we can do intermediate certifying authorities. We can still have our root certifying authority, and we can create an intermediate one for Alice and an intermediate one for Bob. And then things that just trust the root certifying authority, well, Bob and Alice can both talk to it. However, you can also set things up so they only trust the intermediate authority, which means that a certificate that has been generated for a Bob authority will work on anything that trusts root and anything that trusts Alice. But if Bob's actually trying to connect to it, then it's not going to work. So there's a whole lot more command line invocations to run to be able to generate a certificate authority for Alice. But it's pretty much the same thing, right? We simply enable another Pki engine, this time for Alice only. We tune it. We then create a intermediate certificate authority for it. We ask the root certifying authority to sign the intermediate. In other words, this is where we create that level of trust that says this Alice intermediate certificate authority is not only able to generate certificates for itself, it can also generate them on behalf of our root certifying authority. We can then import that signed certificate back into Vault, configure it nicely, and set up all the things that the certifying authority is actually allowed to do. So let's do that. Set up LSCA. Same thing happens. So we have a certifying, we have a certificate that was issued, signed by the local root certifying authority, but it is for the Alice Intermediate Authority. Cool. That works really well. So there is also one with this, we can also do the same thing for Bob, so why not? As you can see, this target directory is now growing. So we have, LSCA certificate signing request and a certificate and a LSCA piece of JSON that kind of had everything there. One of the interesting to think about is, actually we'll get to that. Let's do Bob next. So set up Bob. Okay, so we have, again, we have a certificate that has been issued by a local root certifying authority. It is for the Bob Intermediate Authority. Cool. Let's see if this works. So if we're going to issue Alice with an intermediate, let's issue Alice with a certificate that has actually been signed by Alice's certifying authority. So we can do that with another Vault command. We write, this time around, we write to the Alice PKI. We say, hey, I want you to issue a certificate for alice.example.com, spit it out into a target file. The important thing to think about, though, is when we were talking about certificate chain validation, what we want to do is we want to add the intermediate authority certificate to the certificate chain that Alice is going to present to servers that only trust the root, so that they can verify that, oh yeah, Alice was issued by the intermediate was issued by the root, and I trust the root and everything's okay. So we write that out into the certificate file. So let's do that. Alice PKI cert. Okay. So we have a certificate that was issued by the Alice Intermediate Authority. It was issued for alice.example.com. And when we have a look at the file for Alice, alicepki.cit, you see that it now, rather than the original alice.cit, where it just had its own certificate because it was issued by an immediately trusted root certifying authority, it now has both Alice's certificate and the certificate of the intermediate authority. So we are preserving that trust chain for anybody who needs to verify it. And we can do the same thing for Bob. So again, we have a certificate that was issued by the Bob Intermediate Authority, and it was issued for bob.example.com. Cool. Well, let's see if this works, or if I've actually just been wasting your time. So we have our service that just trusts the root certifying authority. So can we actually talk to it via Bob using mTLS? So the command to do that, again, is a straight up curl command. I mean, you could do this with curl, but we're doing it, this is Go, so we're going to do it with client code. So to actually run it as a client, we basically say run our client main, give it the PKI certificate rather than the default one that it ran with before. Okay, so this one is run ls PKI client. All right, so run ls PKI client. Hello, Alice. Excellent, that works. If we do this for Bob, this should again work exactly the same way. What's happening is that the client is presenting its certificate plus the intermediate authority certificate to our running server. And because our running server trusts the root certificate, it just goes, yeah, sure, no problem, talk to me. So what if we change the server to only run ls? So to do that, we just simply say, you know, Alice, your root certificate is LSCA. Cool. Well, let's run ls PKI service rather. All right, so we can stop our server, make run ls PKI service. Okay, so this thing is now going to be running a server that will only ever trust the Alice intermediate certifying authority. And if Bob tries to connect to it, well, Bob should be out of luck. So let's try that. Alice should get hello Alice. Cool. Bob. No luck. All right. One interesting thing. This error is actually pretty crap. It really doesn't tell you what it's doing, both on the client and the server. TLS client didn't provide a certificate. Well, the TLS client did provide a certificate, it just didn't provide a valid one. It's not the same thing, but thank you very much for cryptic error. At least on the server, you get a slightly better error. On the client, you get a better error that kind of says, hey, bad certificate. Probably a little bit easier to troubleshoot when you're starting from the client, but when you're looking at the server error logs, you've got no idea what's happening there. So that's a little nasty. All right. In the presentation, in the repository, you will find a lot of code. You'll find some bonus code that talks about how to use HA proxy and Nginx to do certificate validation. Because this is a presentation purely about Go, we're going to skip that. We can get to it later if you want to, but for the moment, we're going to skip the whole thing about Nginx and HA proxy. And we're going to go and talk about how to actually create slightly better errors. So what we want to do is we want to inject some code into the certificate validation logic inside the Go server that could potentially give us a little bit more insight as to what's going on when certificate validation fails, and perhaps even give a better error to the client, or at least, you know, TLS client did not provide a certificate is pretty crappy, not very good. So what we want to do, the first thing that we can do is we can actually inject code into the certificate validation logic inside the HTTPS, inside the HTTP stack in a Go server. And you do that by specifying a custom callback to the verify connection parameter. So we have a little function here. This is just the standard. This is the same HTTPS mTLS service that we were running before, except that what we're doing is we're adding this verify connection. One thing that we may want to do is, if you don't, so I guess the problem that I'm trying to solve here is, what if you only want to have like one root certifying authority? You know, one certifying authority rather than a whole bunch of intermediate ones. Well, you can use filtering inside HTTP and Nginx to do that, but you can also do that in Go. So if we go back to our setup and we have a service that goes run mTLS service that Bob can talk to and Alice can talk to, but this thing is only ever looking at the root certifying authority, because we only have one. Assume we only want one root certifying authority. What can we do? Well, like I said, we can interrupt the connection. You can actually get the connection state. So the callback gets given the connection state. You can go ahead and examine the peer certificates inside the connection. The peer certificates really is literally the certificate validation chain as Golang data structures. The first certificate in that chain is the certificate of the client. Any other subsequent certificates are just the intermediate certificates. We're going to ignore them for the moment. They get verified and validated by the mTLS machinery anyway. So this gets called back as kind of a final callback. What we want to do is we want to make sure that only Alice can talk to it. So if the common name, you can check all sorts of things. You can check the DNS subject alternative names, all sorts of things. In this particular case, we just want to check the common name. And if the common name isn't Alice, then we go, well, you're not allowed. Cool. We're doing this in Go. So running that is, again, just a shell command. What we want to do is we want to run the verify connection setup. So we will shut down the server and go make run verify connection. Cool. So Alice should be able to get a hello. Bob, well, Bob is not an Alice. No soup for you, Bob. All right. The client gets bad TLS certificate as an error. Cool, reasonable. Server now spits out HTTP TLS handshake error, bobexample.com is not allowed. Excellent, we can now begin to figure out what went wrong. Something connected to us and we got Bob is not, and the certificate that it got was Bob, and therefore it shouldn't talk to us. So that's actually pretty good. That's already one step up from from the cryptic client didn't provide a certificate error. All right, what can we do any better? To do any better, we have to start and go one level up the stack inside the application and actually use HTTP middleware. HTTP middleware is really just a fancy name of saying a function that wraps a function. So we again have a standard main startup, read the cert file, read the root cert, read your cert files, create a connection. But this time around, when we create a handler, we wrap it inside a middleware. A middleware, again, it's just, a handler that wraps a handler. It sits in between the code that is going to get called when the handler gets invoked and the origin of the request. In this particular case, we can get out of the actual request itself, we can get the P certificates, just like we were doing inside verify connection. They were coming through in the connection state. In this particular case, in Go, which is really, really cool, by the way, the request itself has the P certificates available for you, which is really nice. So we can grab the certificate, we can grab the first certificate, which is the client one, and we can check whether or not it's Alice. If it's not Alice, then we can print out a nice little log line into our own log saying, hey, somebody's doing something that they shouldn't. And we can also specify a little error message that we can send back to the client. So the client, rather than getting this bad certificate error, will actually get a proper response, and it will get a forbidden response because, well, you shouldn't be here anyway. But at least we're trying to be nice and give you a slightly better error. So let's try that. Verify. It's verify middleware. Thank you. All right, server's running. So can Alice do the can Alice do a thing? Yes. Hello, Alice. Cool. We know that this works. At least it works for Alice. Can Bob do their thing? Nope. You cannot be here, Bob. That's really cool. A much better error. You could debug this. You could figure out, hey, something's actually saying I'm not supposed to be here and sending me this error. Inside our server logging, hey, bobexample.com is not allowed. So that's actually pretty cool. It's no longer TLS handshake error because, well, yeah, sure, whatever. Bob is not allowed. Cool. We know that Bob is not allowed. We could add more context to this error message. We could add more fields. We could verify various other bits and pieces. But now this is something that is a little bit more idiomatic to Go, and it's more in our control as engineers, rather than allowing kind of hidden middleware things that sort of happen in the middle. Oh, it defines middleware. Infrastructural middleware to give us failures. So that's pretty cool. Now, in summary, the thing to think about is that this works for HTTP. If you are doing gRPC services in Go, there is an equivalent thing that actually happens there as well. It's a little bit more involved, but the Go gRPC stack can actually also enforce certificates and verify things and do all sorts of other bits and pieces. There's not enough time for this presentation, but in the project for this presentation, there is a link at the bottom to an example gRPC project that I created ages ago on GitHub that has got some experimentation on how to do that for gRPC. So, as a summary, organizations can benefit from mTLS because it allows clients to identify servers, servers to identify clients. You're not flinging tokens around. Tokens generally live forever. They're shared between teams. Even if a team starts off using a token, some good-natured individual trying to do their job. So not throwing stones or shade in a glass house. We'll probably reuse that token for another service. And now I have two services using that token, and you don't really know that that token actually belongs to one particular service anymore. Certificates, if properly controlled, are less likely to be reused between systems. Or at least people think a little bit more about reusing them because it's a certificate. It's supposed to be only be for one thing. One of the nice things about certificates is they can be revoked. The other nice thing about certificates is they expire. So you can use, unlike certificates on the internet, although Let's Encrypt is now popularizing the idea that it rolls certificates every 30, 60, 90 days. You could roll certificates every 5 days. That's really cool. Blast radius of a compromised system now reduces from a year to 5 days. Nice. Languages like Go make this stupidly easy. And infrastructure products like Vault or various other things that you will find on the internet, allow you to have full control and also provide you with very nice graphical bells and whistles and much easier tools to not only administer, but control who can do what, who can issue which certificates, and provide appropriate levels of auditing that will make your security team very happy. That's it. I'm going to stop sharing, and I'm happy to answer questions if anybody has them. Umit, yes, I see your hand up. Just say it out loud, mate.
Yeah, sure. That is a great presentation. Thank you so much for walking us through the example with the mTLS. I was just curious if gRPC stack has mTLS, because I know it's TLS capable 1.3. Are you saying gRPC can communicate with mTLS?
Absolutely.
Okay.
Absolutely. Again, though, with mTLS, so clients and servers using gRPC will send certificate to each other. However, just like we had to do for, they will, if you don't write any other code, you will just get the basics. You'll get the fact that for a server, that the server certificate is issued by a certifying authority you trust, that it has not expired, and then it matches the server's domain IP address, so however you address that server. For clients, it will be the fact that the client is issued by a certifying authority that you trust. If you want to do anything else, then like we had to do with HTTP, you have to write some extra Go code. You could do it inside your Go endpoints, or you could do it as Go middleware, as gRPC middleware and interceptors. The linked project, and I'll put a little link to that here in the chat. This project has examples of how to use middleware to do that.
Great, thank you for sharing.
You're very welcome.
Hey, Tom, I have a question for you.
Go for it.
So in your TLS config, I know you kept it pretty minimal to, for the presentation purposes. Are there any other settings in there that you would recommend that people set when they're configuring their TLS configs for production?
I think the big thing that you want to do is you probably want to remove the ability to create localhost. And unless you absolutely need it, you probably want to remove the ability to actually specify IP addresses. If you're not running if you're running an internal setup that only has IPs, then you will want to allow that. But if you're running an internal DNS, you probably want to get rid of IP addresses.
What about in the actual TLS configs themselves, like in the Go code? For the client and server where you're passing in the certificates, is there anything I'm thinking about maybe min version and other things like that?
You can. So inside when you're configuring the server, you can absolutely harden the servers to specify minimum versions of protocols. You can specify which actual cryptographic algorithms you will be allowed. I think DigitalOcean has a really good thing for, was it Nginx DigitalOcean? There is a, DigitalOcean actually has a little open source project as part of our community called Nginx Config. I'll put a little link to it here. Nginx Config allows you to specify Nginx for to actually create the Nginx config file in a relatively safe and sane way with a whole bunch of presets, especially the presets around HTTPS and security. where you can specify, DNS staplers for Let's Encrypt. You can do referrer policies and all sorts of other things. So that same thing can actually be done in Go, or quite a lot of it can be done in Go. In terms of recommendations, it really depends on what you're using this for. If you're going to put this on the internet, then you want to be as hardened as you can based on the clients that you wish to connect to. So if you know that, for example, you have some corporate clients that can't do latest versions of crypto, then you may allow them to downgrade. But if you're expecting that everybody will use the most up-to-date crypto stacks, then you can harden it very strongly within a corporate environment where the majority of the stuff is actually completely under your control, or at least from a configuration perspective. My recommendation is to go as restricted as possible. Some of the there are some very well-known attacks against cryptographic libraries that have been used in all the versions of HTTPS protocols. You will absolutely wish to not use those, but also then restricting yourself to just using the most secure and hardened versions of the protocols is probably a really good idea within an intranet. For public systems, you have to be able to accept your lowest common denominator, and how you choose that is based on the survey of the customers that you wish to have and their capabilities.
Great, thanks. Sounds like we should. It looks like we should add a Go example to that link you posted, because I think there's a Python one.
There's we should absolutely be able to do that. The Python one's pretty cool. So this is one of, there are a number of services like that on the web that will allow you to specify configure Nginx. There are ones that will allow you to configure Nginx or Apache or whatever. I have not seen one that will allow you to actually create a configuration for a Go HTTPS server. So that would be a really cool addition that we could do. That would be a lot of fun.
Yeah, I think I was actually just looking it up. I think Mozilla actually has one. I don't know how good it is or not, but
Mozilla Go HTTPS config. Let's have a look. Oh, look at that. I'm just going to click on that link. Give me a second. Wow. Yeah, look at that. Yep, they do it. Look at that. Minimum version, pick cipher suites. Consider setting read timeout, write timeout, and idle timeout. Absolutely. You have to, unless you're doing things, well, actually, even with WebSockets have a habit of dying. So most WebSocket setups actually will have some form of a keep alive. So yeah, having read and write and idle timeouts is a really good idea, because you don't want to have these resources open forever. Where at that point, this becomes an intersection between security and infrastructure and SRE and reliability. But yeah, this one's actually pretty cool. And they're adding they're one of the really interesting things, they're adding the strict transport security header. The other thing one thing that they're not adding is the report URI headers, although reports URI is being deprecated, but it's being replaced by something equivalent. So that's pretty cool.
Cool, thanks.
What's it called? There is actually a thing that I've been showing people when we're talking about HTTP security, which was, there is this, but where is it? Sponsor. So for Go users, there is this thing called Unrolled Secure, which is a nice piece of middleware that you can actually add into your HTTP stack that will set up an awful lot of really good security patterns for your HTTP hosts, for HTTP servers written in Go. I'm trying to find the thing that I've been. I may have lost the link to it. No, I have it. Bingo. So App Canary created a blog post that talked about HTTP security headers and their current recommendations. It's still pretty current. It was done in 2017, but it is still actually pretty good. And if you're thinking about hardening web servers to provide HTTP security headers, this is a really good thing to actually look at. They also provide examples of how to do that for Go, for Express, for Rails, for Django, Nginx, Apache, Varnish, whole bunch of things. So it's a very good resource if you're beginning to think about HTTP security on the web, especially on the public web. Although nowadays the threat models for intranets are becoming pretty much similar to the threat models for public internet, because most of the time you run things on clouds like DigitalOcean. And even though you may be running it inside a virtual private cloud in a virtual private environment, misconfigurations will happen if your systems aren't secure. You know, if they're, for want of a better term, if they're a turtle, hard shell and soft middle, well, somebody coming in is like sticking a blender into the turtle. Not a really good mental picture. So, any more questions? Anybody would like to know anything? Okay, I'm going to consider this presentation done. If you would like to give me feedback, you can do so via email. You can do so via Twitter, or you can do it via Ross or in any other way, shape, or form that you desire. I would like to know your feedback. These presentations only work because people are interested in them. If I am a boring person and you never wish to hear from me again, that's easily done. Thank you.
Thanks, Tom. Really appreciate it.